All right, so I'm going to draw a picture of a circuit here. Here is some source voltage Vs connected to the transformer, like so, where we have some inductance for coil 1 that we'll call L1. Here is the secondary side of our transformer with some inductance L2. And then our secondary is connected to some load impedance ZL, like so. I'm going to define my voltage V1 with this polarity, my voltage V2 with this polarity, my current I1 with this polarity, my current, I1 with that direction and I2 with this direction. And I'm going to put these parallel lines here in the middle. So effectively, whenever you see anything that looks like this thing I'm boxed in here in the middle, we're dealing with an ideal transformer. What those two parallel lines represent is that the coils are wrapped around a common ferromagnetic core so that the coupling is perfect. Okay, so that's actually one of the constraints for an ideal transformer. Okay, so an ideal transformer will have R1 is equal to R2 is equal to 0, meaning that our coils don't have any losses associated with them, so they exhibit no resistance. And our coupling coefficient K will be exactly equal to 1, meaning that both of our coils are perfectly coupled together. So in the event that K is equal to 1, what should our mutual inductance be, right? So hopefully we remember from our last class meeting that K was defined as M over the square root of L1 times L2. So in an ideal transformer, M must simply be the square root of L1 times L2. Doing a trivial amount of algebra there. Okay. So the inductance of a solenoidal coil, we talked about this, I think, 3 class meetings ago, is proportional to the turns, or excuse me, the number of turns in the coil, right? So we could say that L1 is going to be equal to some constant value K times N1 squared. And similarly, L2 would be K times N2 squared, where the value of K here isn't particularly important. It's just glossing over the electromagnetic relationships that we're not really concerned about right here. Okay. So I could express the ratio of L2 divided by L1 as the square of the turns in inductor 2 divided by the square of the turns in inductor 1, and I'm going to call this A squared. Okay. So A would then be simply the ratio N2 to N1, or the square root of L2 over L1. And this is what we call the turns ratio for our transformer. And it's going to be probably the most important parameter that we're dealing with when we have an ideal transformer, right? So let me quickly depict here. N1 has, or excuse me, coil 1 has N1 turns and coil 2 has N2 turns. Okay. So we're going to play around with these relationships and try to figure out what's going on with the voltages and currents in this system. Okay. So if I were to express my voltage V1 here, I would have J omega L1 times I1 plus J omega M times I2 based on the location of the dots and the direction of the currents that we have. Everybody okay with that? This could be written as J omega L1 I1 plus J omega square root of L1 times L2 times I2, simply substituting in the fact that for an ideal transformer, our mutual inductance is nothing more than the square root of L1 times L2. And now I'm going to play around with a little bit of algebra here, right? So let me do this in a different color so you can see what's happening. So if I have the square root of L1 times L2, this is the exact same thing as the square root of, make sure I'm doing it right. The square root of L2 divided by L1 times L1 squared. Are we okay with that? Anybody have any problems with that algebraic leap? Okay. Well, this is nothing more than my turns ratio times L1. So I could say that I have J omega L1 times I1 plus J omega A L1 times I2, or J omega L1 times I1 plus A times I2. If we wanted to write our voltage V2, we would have J omega L2 times I2 plus J omega M times I1, once again based on the directions of current flow and the location of where we've chosen to place our dots, right? So once again, I'm going to play around with a little bit things here. So if M is equal to the square root of L1 times the square root of L2, and A is equal to the square root of L2 divided by L1, then A times M is L1 times L2 times L2 over L1, all under the square root sign. These guys cancel each other out, so I have the square root of L2 squared, or just L2. So effectively, anytime I have L2, I could replace it with A times M. Okay, so I'm going to do that here. So J omega L, excuse me, A times M times I2 plus J omega M times I1. Well, up here, we figured out that M was the same thing as A times L1. Okay. So that's going to give me J omega A squared L1 I2 plus J omega M, excuse me, J omega A L1 times I1. And we can group things here. J omega L times I1 plus A I2. And this whole thing will be multiplied by a factor of A. Are we okay with the algebra that I've done here? So what's the relationship then between the voltage V1 and the voltage V2 for this ideal transformer? Yeah, so what we should see is that V1 is equal, actually, excuse me, got it backwards here. V2 is equal to A times V1, or another way to put this, it would be that A is equal to V2, sorry, divided by V1. So our turns ratio tells us how the voltage is going to change from the primary side to the secondary side and vice versa. Yes, sir. Yes, that should be an L1 right there. Thank you. Okay. So this lends us to a voltage relationship for a transformer, right? So if A is greater than 1, we have what's called a step-up transformer, because the voltage on the secondary side will be greater than the voltage on the primary side. And if A is less than 1, we'll have what's called a step-down transformer, where V1 will be greater than V2. So do any of you guys have any idea where step-up or step-down transformers might be used? Absolutely right. So if we were to look at the voltage on the transmission lines that are coming from the substation north of town here, the voltages leaving that substation are, I believe, 13.8 kilovolts RMS. But in our outlet, which is connected to that substation, we only see 120 volts RMS. So there obviously has to have been some sort of step down transformer somewhere between where we are getting our power, that substation, and here. And those are those transformers on the poles that you see outside. Those are literally step down transformers that are converting that 13.8 kilovolts RMS into a 208Y 120 voltage accessible by all the building stuff like that here on campus. What about a step up transformer? Yeah, so effectively, when we generate voltages using three-phase generators and all that kind of stuff, we're probably not able to generate hundreds of kilovolts of voltage. So we typically generate something on the order of tens of kilovolts of voltage in our power plants and stuff like that. We step it up to really high voltages, as much as 250 kilovolts RMS to transmit it over very, very long distances. And then once we hit a substation, we step it down to a safer level for being around humans. And then once we get it to a household, we step it down to an even safer level for people to be able to interact with regularly. Absolutely right. So step up and step down transformers form the fundamental basis of power distribution in every industrialized country. Okay. All right, so let's look at the power supplied by our primary side here, right? So on our primary side, which we're going to call 1, must be equal to the power on the secondary side, right? We have a closed system, so power in must be equal to power out. So that would mean that V1 times I1 conjugate must be equal to V2 times I2 conjugate. We know that V2 is equal to A times V1, right? So what's the relationship between our currents? Well, we should see that I1 is going to be equal to A times I2. Or another way to express this would be that A is equal to I1 over I2. So we have the exact inverse relationship to be able to transform currents. Does this make sense? It should. If we step the voltage up, we should have to step the current down in order to keep the power constant. Right? So any step up voltage transformer is actually a step down current transformer and vice versa. That's also another one of the reasons why we choose to use transformers and transmit power at extremely high voltages over long distances. The higher that we can get that voltage to be, the smaller the amount of current has to flow along the wire, which means we can use smaller wires, which are cheaper. And it also means that less losses are going to occur due to the wires heating up because they're carrying less current. Right? So our I squared R, or our copper losses, will be smaller the higher we can get our voltages in a distribution system. Okay, so we have some understanding of the fundamental relationships here. Now let's talk a little bit about input impedance, like we talked about the other day. So when we had a practical transformer, our input impedance was formed from the primary loop impedance and then some scaled version of the secondary loop impedance, right? It was omega squared, m squared divided by the secondary loop. Things are going to be even easier. It's now just going to be related to the turns ratio. So if we look at our diagram up here and we were trying to find the input impedance seen looking in to the primary terminals of our transformer, what we would have is the exact same relationship we had in our last class meeting. Zn is equal to V1 over I1, which is going to be 1 over A squared times V2 over I2 from these relationships, right? We can see that V1 is equal to V2 over A, and we can see that I1 is equal to A times I2. Putting those two relationships together, we get this. Well, V2 over I2 is nothing more than our load impedance. So we're going to have our load impedance ZL divided by our turns ratio squared. And that is our reflected input impedance. That's all we see, right? So effectively, let's work a problem here. So let's say that I have the following circuit. (12 ∠0° voltage source connected to a 1 kilo ohm resistor connected to an ideal transformer that has a turns ratio of, so 1 turn on the primary side for every 4 turns on the secondary side. Our secondary winding is connected to a 32 kilo ohm resistor. We are trying to find V out. Just to be clear here, I'm going to define V1 here and V2 here. I'm going to leave that line there. So looking in to the transformer just after this 1 kilo ohm resistor, what we would see would be our 32 kilo ohm resistor divided by our turns ratio, so 4:1 or 4 squared. What we would see would be a 2 kilo ohm resistor from the perspective of our primary side. So effectively, we have 12 ∠0° connected to a 1 kilo ohm resistor connected to a 2 kilo ohm resistor. And this is our voltage V1. So what should V1 be? You could do it that way, or you could use voltage division. Hit me with a number. Or tell me how to do voltage division and I'll write it down and I'll tell you the number. Sorry, what? It is either 8 or 4. Which one is it? You're thinking incorrectly. So remember Ohm's law, right? V is equal to I times R. So if we're finding the voltage drop over the larger resistor, the voltage drop should be the larger one. So just to move things along here, we'd have 12 angle 0 volts times 2 kiloohms over 1 kiloohm plus 2 kiloohms would be equal to 12 times 2/3, which is 8 angle 0 degrees volts. So how do we find our output voltage? Well, that's the great thing about an ideal transformer. V2 is just equal to A times V1, because our 32 kiloohm resistor is literally in parallel with the secondary windings. That means that V out is just going to be equal to 4 times 8 angle 0 degrees volts, or 32 kilovolts. Let's make this a smidge harder, not by much. Okay. So let's say that I have a 24 angle 0 degrees volt source here. I'm sorry, what? Oh no, volts. A 1 kiloohm resistor here. Here's my transformer, which has a turns ratio of 1 to 2. So I want to know a couple of things here. The first thing I want to know is the complex power supplied by my voltage source. Okay. Another thing that I want to know is the voltage drop across my 16 kiloohm resistor. And another thing that I want to know is the impedance seen by my voltage source, which honestly is probably going to be the first thing that we do, because it'll make solving for the other part easier. Okay. So a question like this and a circuit like this is absolutely what I intend to ask you on your exam on Tuesday. Just to be very, very clear here. So this is what I'm expecting of you to be able to do with respect to an ideal transformer circuit. So how should we begin? I gave you guys a big hint. I think we should probably find the input impedance first. So any thoughts on what that's going to entail? So what do you mean by the load impedance? Okay, so the impedance of the secondary. All right. So I'm going to take what James was saying. The impedance of my secondary, so that's 16 kiloohms minus J8 kiloohms divided by what? 2 squared. Am I going to see anything else? I disagree. What about my 1 kiloohm resistor? So where am I looking in from? If I'm looking in from the voltage source, I'm definitely going to see that 1 kiloohm resistor in series with the reflected impedance of the secondary. Up here, I was looking in specifically through the transformer terminals, right? So when I did my analysis, I had that 1 kilo ohm resistor in series with that reflector kit. If I'm looking from further behind or closer to the voltage source, I need to take into account everything the voltage source sees, which means I would need to put 1 kilo ohm in series. Does that make sense? Okay. So, what's 16/4? 4. What's 4 plus 1? Not a trick question. 5. All right. So we have 5 kilo ohms real. What's 8/4? 2. So 5 minus J2 kilo ohms is our input impedance, as seen from the voltage source. Anybody have any problems with that? Okay. So let's take a crack at the complex power here. Actually, I'm going to make one very slight change just so we don't have to do any extra math. I'm going to call that an RMS voltage so we can be lazy and not have to remember that factor of 1/2 that we would have needed if I didn't do that. So, all right. So I'm trying to find the complex power supplied by my voltage source. What 2 pieces of information do I need? Voltage and current, right? Well, realistically, actually, I don't even need the current anymore, although we could easily find it. That's what my initial thought was just find the current, but we could actually just use that input impedance as well, right? So S of VS is going to be VS times IS, and let me say what this IS is here. Conjugate, which would be VS times VS over Zn conjugate, or the magnitude of my source voltage squared divided by the conjugate of my input impedance. So that would be 24 volts RMS squared divided by 5 kilo ohms plus J2 kilo ohms. Remember, when I take the complex conjugate, I change the sign on the imaginary part. And so let's throw this into my calculator. 24 squared divided by 5,000 plus 2,000 I. I get 0.107 with an angle of negative 21.801. Degrees volt amperes, which would be the same in rectangular form as 0.099 minus J 0.03040. Right? So there's our complex power supplied by our voltage source. So the last thing that we need to figure out is the voltage drop across our 16 kilo ohm resistor. How are we going to do that? Pretty similarly to what we did in the last example problem, but we are going to have to pay a little bit of attention, right? So I need to figure out what this voltage V1 is so that I can figure out what this voltage V2 is so that I can figure out what I have labeled as V naught. Okay? So how am I going to find V1? Sorry, what was that? Voltage division, sure. So I think V1 should be 24 angle 0 degrees volts RMS times, let's look up here, 4 minus J2 kiloohms over 5 minus J2 kiloohms. Or 19.931 with an angle of negative 4.764. If I've done this correctly, which I believe I have, but if you guys have a different suggestion, I'd be willing to hear it. How do I find V2? What? Multiply by the turns ratio, A, yep. So V2 is just A times V1. So multiply that by 2. We would get 39.862 with an angle of negative 4.764 degrees volts RMS. And lastly, how do I find V naught? Another voltage divider. Why the heck not, right? So that's just going to be V2 times 16 kiloohms over 16 kiloohms minus J8 kiloohms. So I get to be 35.654 angle 21.801 degrees volts RMS. There we go. Anything wild, crazy about that? No. Ideal transformers make lives much, much easier, right? When we get into our second power class next winter, what we're going to do to be as lazy as possible, actually, is when we develop our model for magnetic circuits and transformers and stuff like that, we are going to include an ideal transformer in our model for a practical transformer so that we can easily reflect connected impedances back and forth between the primary and secondary, just to make our lives a little bit easier. So we're effectively going to combine these two topics into one single model that can be used to account for any type of losses and things like that we might see in a real transformer. All right, so that's the last thing that I wanted to talk about for today. So review time. What's up? All right, so I'll talk. I think I'm going to give you guys 3 circuits, okay? So the first circuit is going to be something nasty, probably like homework number 7, problem 4, with the expectation there that you only need to be able to write the equations. That being said, I'm going to specify the directions of your currents and the polarities of your voltages. So you don't get to do it. So you have to be able to use that little table thing that we developed to know when things are going to need to get a minus sign versus when things are going to need to get a plus sign, instead of setting it up so that everything always gets a plus sign. Okay. So that's how I'm going to test you on that particular material. Does that seem unreasonable? All right. So that's going to be approximately 30 points because I'm thinking there's going to be 3 coupled inductor pairs or whatever. And so 10 points for each one of those equations in total. Then I'm going to give you a circuit similar to one of the examples that we worked in class on Tuesday, where you should be able to use the input impedance and stuff like that in order to calculate the currents. So very, very similar to the example problems that we worked. So just as a heads up, something like this. You have some source voltage. We have some impedance Z1 here. This is ZL1. I'm arbitrarily going to put the dots on the same side, but that could be different. Here's some impedance ZL2 here. There's coupling between these coils. I could give this to you as either giving you K or some ZM. Same, 2 different ways of expressing the same information. Here's some impedance Z2. Here's some impedance Z load. And you need to be able to calculate this current I1, and just for the simplicity's sake, let's call it this current I2. So I'd probably break this up into 3 parts as well. You need to find the input impedance seen by the source so that you can solve for I1, and then using I1, how would you solve for I2? So 3 steps, 30 points as well. Okay. And then your third circuit is going to be practically this with different numbers. Okay. And 3 parts. I'll be nice and I'll give you 10 points for just writing your name down correctly. Yes. So something like some of those ugly homework problems? Absolutely. So I'm just going to flip here and find something gross. I'm not sure if that one's gross enough. No, something pretty, I mean, different numbers like that might be an impedance instead of just 1 kilo ohm or something like that, but this basic format with different numbers, probably asking you for almost exactly the same pieces of information. I might, the only thing that I could think of that I could do differently here, or may do differently here, is ask you for the input impedance looking into the transformer as opposed to from the perspective of the voltage source, which would just mean you would ignore the 1 kilo ohm resistor because you're looking to the right of that. But other than that, it could be effectively the same thing. All right, so I'm just going to take this circuit from this textbook, and then Matthew, tell me if I need to make it worse. So say 30. 20. And then for this particular problem, they were trying to find this voltage V out. And this inductor is coupled to this inductor by a mutual inductance of J 10 ohms. So is that gross enough or do we need more? So let's call this J 30 and dot on top of bottom. All right. So what's the coupling going to be between these two? Oh, let's not make it J30 because there's already another J30, so that'll be confusing. Let's call it J10. Well, nope, let's call it J15. So what's the coupling going to be? Make a number. Yeah. And let's say that these two also have coupling. Let's call this J8. Okay. Is this gross enough or do we need to make it grosser? Okay. So let me think about things here. No, I'm not going to think about things at all. You guys tell me polarities. Okay. So what should the polarity be for the J30? Positive on top or positive on bottom? Okay. So let's call that V1. What about for the J15 ohm one? Positive on top or bottom? All right, J15, positive on top or bottom? Entirely arbitrary. All right, and then for the J20, positive on left or right? Okay. For my mesh current 1, clockwise or counterclockwise? Mesh current 2, clockwise or counterclockwise? Doesn't matter. Okay, so let's start with V1. Okay. So we are going to have a self-inductance term. So that's going to be J30 ohms times I1. And then we are going to have two mutual inductance terms. So one of them is going to be coupled to the J15. So that coupling between those two was J20. And the total current flowing through there is I2 minus I1. And then we're going to have the coupling between coil 1 and coil 3, which is J10. And current flowing into the dot is I2. So now let's figure out the signs, okay? So in order for our self-inductance term to be positive, the positive polarity terminal needs to be at the dot, and the current needs to be flowing into the dot, or the positive polarity terminal needs to be at the undotted terminal, or the undotted end of the inductor, and the current needs to be flowing into the undotted end. We don't have either of those cases, right? The positive polarity is at the undotted terminal, but the current I1 is flowing into the dotted terminal, which means we're supposed to have a negative sign. All right. Now let's talk about our mutual terms. Okay. So we have established that the positive polarity terminal is at the undotted terminal. Okay. So that means for our mutual terms to be positive, we need the current to flow into the undotted terminal. Okay? So the current flowing into the undotted terminal of that second one is I1 minus I2, which means if I put a negative sign here, that takes care of that. And the current flowing into the undotted terminal of coil 3 would be negative I2. So I put a minus sign here to take care of that. So to make your life the easiest when solving a problem like this, it's usually the best idea to put your dotted polarity, to put the positive polarity terminal with the dot in every case. And then it's whatever current flows into the positive polarity terminal will give you positive signs for everything. Yeah. But something like this is exactly what's going to be on your test, where I'm making you do it to where it's not all just going to come out to be positive signs. So let's look at V2 here. So we have a similar case. So we're going to have a self-inductance term for this J15. We're going to have a mutual inductance term between coils 2 and coil 1. So that's going to be, make sure I'm giving myself enough room here. J20. We'll talk about the currents in a moment. And then we have a mutual inductance term between coils 2 and coil 3. It's going to be our J80. Okay. So now let's think about how to make these positive, just for the sake of argument, right? So what is the current flowing into the undotted terminal of the J15 ohm inductor? Yeah, actually, I may have made a mistake on the I2 minus I1 part, because recognizing that those currents are in the opposite direction. So let me, because they're defined the other way, they should be adding together actually. Let me put a plus sign there. Sorry about that mistake. I get so used to having the currents all flowing clockwise or counterclockwise that when we mix them up, I sometimes forget to take into account their sign. All right, so I2 plus I1 is flowing into the undotted terminal. So I1 plus I2 here will give me a plus sign out here. Then I have my coupling with coil 1. So because the positive polarity terminal, let me do this. The positive polarity terminal of V2 is associated with the undotted terminal. Now I need to know what current is flowing into the undotted terminal of coil 1. So what would be the current flowing in? Negative I1, right? So negative I1 here would give us a plus sign there, which is the exact same thing as just putting a negative sign here with positive I1 there, right? And then we need the current flowing into the undotted terminal of the J20 ohm inductor at the top right. That's going to be negative I2. So we're going to have minus I2 like so. For V3, I2 is flowing into the dotted terminal. So we're going to have positive J20 times I2. Coupling to coil 1 is going to have a J10 term, sorry. And the current I1 is flowing into the dotted terminal. So that's going to be an I1 and a plus sign here. Then we're going to have our coupling with our second coil. So that's going to be our J8 term. And then the current flowing into the dotted terminal would be negative I1 plus I2. So I haven't put the videos online, but I'm going to do that today. When we first covered this material, which I think you may have been absent for, I literally gave you guys a table of the rules for doing this. I would highly suggest you kind of write that down on your equation sheet for the exam. And then once you have that, it's fairly straightforward, right? So there are always two criterion that you need to look for: where the positive polarity terminal of the voltage is with respect to the dot for that particular inductor, and then the direction of the currents flowing into the dotted things. Probably the most confusing thing here is when we're, so let me see if I can spell this out as obviously as possible. So let's look at just this first term right here, so I can re-explain why they all have negative signs, okay? So this first negative sign comes from the fact that the positive polarity terminal is on the undotted sign, but the current is flowing into the dotted terminal. So because they're opposite, we have a problem, we give it a negative sign, okay? For the second term, because the positive polarity terminal of V1 is at the undotted terminal of coil 1, what we're trying to find is the current flowing into the undotted terminal to give us a plus sign out here. Well, the current flowing into the undotted terminal is I1 plus I2. So actually, this one should be a plus sign because the current flowing into the undotted terminal is I1 plus I2. So that was me messing that up a moment ago by not recognizing that the currents were flowing in the same direction through that. So it's a good thing we went to look at this. All right, for our third term there, once again, because this plus sign is associated with the undotted terminal, we're finding the current that flows into the undotted terminal of V3 or of coil 3, and the current flowing into the undotted terminal is negative I2, and then I move the negative sign over. Yes. It's the voltage on the first coil. Exactly right. That's the most confusing part. We're just looking for the voltage polarity on coil 1, and then how the current is behaving for coil 2 or coil 3, in this case, in a 3-coil system. Absolutely right. So all of these signs are depending on the voltage for coil 1. And then the self term is the current for coil 1. The first mutual term is the current for coil 2. The second mutual term is the current for coil 3. Yep. Mm-hmm. I want you to just write these equations. Yeah, that other stuff is trivial. And I mean, that might sound flippant, but like around this thing, what I would do if I were writing my KVL equations, so if I'm interested in actually solving this, to me, for my first equation, this would just look like, sorry, that should be a 1. V1 plus 20 ohms times I1 minus V2 plus 120 angle 0 degrees volts is equal to 0. And then you would literally just substitute things in. The hard part's already done. So I'm more concerned with you being able to write those 3 voltage equations to plug into the KVL later than write the actual KVL equations, which I've made you do numerous times throughout this class. Yeah. So if you can do this part correctly, the other parts you need. So that's why for the test, I'm only concerned with writing our voltage equations across your inductors. There's also, doing it that way, less chance for you guys to make simple algebraic mistakes and all that kind of stuff like that. So I'm really just testing you on the thing that I'm interested, whether or not you can do, not can you do a little bit of algebra and make sure to carry through all the negative signs when you're subtracting a voltage. That's boring. I mean, I could, but you can just do the homework with like the homework problems that you have. Choose a different thing than you did the first time you did it and make sure you get the same answer. If you did it correctly. Or if you haven't done the homework yet, which some people haven't, do the homework, but don't set up the signs and the positive polarity terminals and the current directions in the easiest possible way. The answer is going to be the same either way. So, I mean, you can, for a 3-coil system like this, there are, let's see, so you have 2 options for voltage 1, 2 options for voltage 2, 2 options for voltage 3, 2 options for the current I1, 2 options for the current I2. There are literally 10 different ways that you could work the problem, but the answer should be the same all 10 ways. So I'm going to be lazy and make out your tests instead of making out practice problems for the test. What else do we need to talk about? Sure. So Logan, what's my voltage going to be? What is my impedance Z1 going to be? Give me something in rectangular. What's the impedance of my first coupled coil going to be? Dot on top or bottom? What's the impedance of my second coupled coil going to be? Dot on top or bottom? What's my mutual inductance going to be? It should be less than, yeah. All right, what's my impedance Z2 going to be? What's my load going to be? Just give me a resistor value. I'm going to do 2 ohms because it'd be weird with 3 ohms and 5 ohms and then a kilo ohm size resistor. That would be awkward numbers. All right, and here's I1. Here's I2. So my input impedance, Zn, should be the impedance of my primary loop. So that is going to look like 3 plus J22. And then I'm going to have omega squared m squared. So that's going to look like 10 ohms squared, the impedance of my secondary loop, which is going to look like 7 plus J22. So I'm going to come up with a number there. 3 plus 22i plus 100 over 7 plus 22i. 18.386. Angle 76.432 degrees ohms. So I1 should just be Vs divided by Zn, 120 angle 0 degree volts, divided by that number that I'm too lazy to write down again. 6.527 angle negative 76.432 degrees amps, sorry. And now the only thing that I would have left to do would be to find the current I2. So I'm going to need to write my equation. So I'm going to call this voltage V1. And I'm choosing to put the positive polarity terminal at the undotted terminal because I know that the current is flowing into the undotted terminal, so that this is going to be a positive self term, right? So V1 is going to look like J20 times I1 plus J10, and I2 is flowing into the dotted terminal, I2. So using this, I would have 120 angle 0 degree volts is equal to 3 plus J2 ohms times I1 plus J20 I1 plus J10 I2. So that I2 would be equal to 120 angle 0 degrees volts minus 3 plus J22 I1 all divided by J10. 2.827 angle 121.218 degrees. So just to be clear, for a circuit like this, first step, find the input impedance. The input impedance does not care what the dot configuration is. Okay? At all. So it's just your primary loop impedance. So that's just all of the bits in the primary loop, add them together. Then it's going to be omega m squared, which is just the part of your mutual that doesn't have a J, square that, divided by all of the series impedance of the secondary loop. Okay? That's going to be your input impedance for a problem like this 100% of the time. The current flowing through the first loop, I drew it in that direction so that I1 would simply be Vs over Zn. If the current were flowing in the opposite direction, it would be a negative sign out front. Once we know I1, we simply write a KVL equation around our first loop, taking into account the mutual inductance. So the exact same thing we were doing in this previous example. The only thing we don't know is I2. So we just solve algebraically for I2. Once we know I2, we could then calculate the voltage drop across the output, load resistor here, the 2 ohm resistor, or we could figure out, the power delivered to the load by using our complex power relationship, any stuff like that. But the process is the same. Find Zn so that you can find I1, so that you can find I2, and from that point, you know everything that you could possibly know about the circuit in one minute. Was that helpful, Logan? Okay. What's next? So looking in from the secondary side, so are you trying to find the output? Okay, sure. So Bailey, give me a voltage. Give me an impedance. J10? What's my turns ratio? 1 to 4? Give me another impedance. You guys like inductors a lot. Keep giving me inductors, never capacitors. Give me a load resistance. All right, so you want this. Well, this is easier than what we did a moment ago. This is literally just going to be the impedance of the secondary loop. So that's 15 plus J7 ohms divided by 4 squared. So 15/16 plus J7/16. Oh. If we were looking in from here, the voltage source, I'm going to call this Vn prime. It would literally just be J10 plus the other thing. And then from this point, we would do, depends on what we're trying to solve for, but we would effectively do the same period step. So you just add effectively you'd just be adding the primary loop impedance in as well, because the voltage source sees the primary loop impedance and the reflected secondary loop impedance, which is exactly what we were doing here. If you look in at the terminals of the transformer, and it's an ideal transformer which doesn't have any internal impedance itself, all you see is the reflected secondary impedance. Anything else? All right. So I'm about to go to my office. I've been working on a homework set number 8, which will include problems dealing with the K factor, the coupling coefficient. So I'm going to give you an example of using that as opposed to just giving you M and then asking you to solve a problem. I'm going to give you a homework problem like this one that you have to solve on your own so that you can get some practice and all that kind of stuff. And I'm going to, give you a homework problem like this one so that you have some practice, so that effectively everything that you've seen or you will see on this test, you will have a homework problem associated with it with a known answer so that you can practice. Does that sound fair? Okay. The homework set's going to be due on Tuesday, the same day as most of you are taking your tests or whatever. Does that seem unreasonable? You should be doing it to study for your test anyway. So, all right. So I'm going to get the videos up. I'm going to get the homework assignment up. Both of those things are going to happen today. Yes, sir. Test is Tuesday.